Okay, guys. So in the last class, we had an introduction to molecular orbital theory. Okay, and one of the reasons for us to be learning this topic here is because you will need to know MOT for organic one and organic two. So once again, our purpose is when you guys get to organic, you got a pretty solid foundation in molecular orbital theory so you can apply that to organic molecules. So what I discussed in the previous class, this here is a summary of that. First of all, we define what was molecular orbital theory. So the main difference, guys, between MOT and valence bond theory is that in molecular orbital theory, the electrons are delocalized. Okay, that's the fundamental difference. So when you compare, you think about valence bond theory, and once again, I'm going to type it on the chat. If you think about valence bond theory, you're talking about localized bonding. So you're talking about mainly bonding happening. So localized bonding, so bonding taking place between adjacent atoms. Okay, that's what I mean by localized bonds. And in this regard, for valence bond theory, we learn and we define what was a sigma bond, what was a pi bond, and then we talk about hybridization, how the atomic orbitals of an atom will be hybridized before bonding, right? And that's how we learn to classify different hybridization states in every atoms in organic molecules, right? Now in molecular orbital theory, we are looking and giving a different perspective to bonding, okay? So it's a different theory. Why is that? Because valence bond theory is great for most examples, most molecules, but there are a small group of molecules that cannot be explained. So, and what I mean explain is their structure, their electronic structures cannot be explained based on valence bond theory. Okay, that's why molecular orbital theory is pretty helpful. Besides that, molecular orbital theory is based on quantum mechanics, so it's like giving a quantitation, numbers, equations to all these orbitals and energy levels. So that allows a much more accurate definition of the electronic distribution of these molecules. So when we think about MOT, guys, electrons are delocalized. So we are thinking about the electrons in atoms are combined to form a new molecule. And now in this new molecule, the electrons will be located in molecular orbitals. And these molecular orbitals are going to be occupying the entire space of the molecule, okay? That's what I mean by delocalized. We're not thinking about a bonding between the carbon and hydrogen forming a sigma covalent bond. We're thinking about atoms coming together to form a molecules, electrons being now in molecular orbitals. Now, I started last class explaining how can we build molecular orbitals? Where are these orbitals coming from? How can we quantify them? So molecular orbitals arise from adding together atomic or hybrid orbitals. And remember how we said that electrons have wave-like properties and how we said that orbitals are simply uh, wave functions, right? So we talk about finding electrons in orbitals. We talk about probability density. That's what we refer to. So what we're talking here is about wave functions. So we are combining the wave functions of the atomic orbitals or of hybrid orbitals, we'll see that later, to form new molecular orbitals. So linearly combining, uh, and that's what I said also, linear combination of atomic orbitals that leads to molecular orbitals, okay? And then we also discussed in the last class how is this linear combination actually done, right? So we talk about the amplitude of the waves. So the wave function, we discussed that how the positive amplitude, the negative amplitude, and the square of the wave function is actually the probability density. And then we talk about how can we combine orbitals, what is exactly the linear combination of atomic orbitals to form molecular orbitals. And I said in class that because orbitals, if you're combining two orbitals, these two orbitals could be in phase, meaning that they are actually having the same phasing as shown here in the picture, or they could be out of phase. So as you see here with opposite phases, right? So you have two situations. One situation in which the two orbitals to be combined are both in phase, and another different situation in which the two orbitals to be combined are out of phase. Because of that, when you combine two atomic orbitals, you always get two molecular orbitals, right? One is the result of the in-phase combination shown here on the slide in which the amplitude is actually reinforced. And the second one is the subtractive effect of the out-of-phase combination of these two orbitals. And we learned in the past class to name the orbitals resulting from the in-phase combination as bonding molecular orbitals, and the orbitals resulting from the out-of-phase combination anti-bonding molecular orbitals. So these are simple rules, math principles that we need to know before we go ahead to build these molecular orbitals diagrams. Okay, so combining once again n atomic orbitals will lead to the same number of molecular orbitals. Half of these orbitals will be bonding and the other half will be anti-bonding. Why? Because they are the result of combining these orbitals, atomic orbitals, in phase and out of phase. We also arrange molecular orbitals in order of increasing energy. Molecular orbitals are also quantizing energy exactly as atomic orbitals. And because of that, to fill up a molecular orbital diagram, we basically follow the same rules that we learned before for atomic orbitals. So we fill from bottom to top, two electrons are placed in one orbital, and both electrons will have pair spins. So we started looking at different examples in the previous class. One simple example that I gave you was combining two 1s orbitals, okay? So the combination of two 1s orbitals in phase, as shown here, leads to, once again, a bonding molecular orbital, which looks like this. And we call these bonding molecular orbitals a sigma, because sigma stands for cylindrically symmetrical around the bond axis, right? So because of the shape of this new orbital, we label them. We label it as sigma bonding molecular orbitals. And the combination of two 1s orbitals, when they are out of phase, because this out of phasing in between these two orbitals will lead to an area in which both wave functions cancel out. So that means the wave function value is zero, an area with zero electron density, right? That's a node, that's another plane. So that's an anti-bonding orbital, okay? So that's how we combine 1s and 2s orbitals. So I'm gonna go and change the application and I'm gonna do a small problem with you guys very quickly. So we use it as a reminder of what we learned in the previous class. In the meantime, if you guys have any questions, feel free to ask. Okay, so let's build the molecular orbital diagram for boron. I'm sorry, give me 1 second. So first of all, let's build it for helium. For the molecule of He2, atomic number of helium is 2. So let's build the molecular orbital diagram for He2, guys. I'll show you later. So right now I want you to focus on writing and developing this by yourself, okay? We'll do this right now, here. Okay, can you guys type on the chat what's the electronic configuration of uh, make it larger? Absolutely, not a problem.
Thank you, Professor.
Okay. So can you guys type on the chat what is the electronic configuration of He of helium? Atomic. So that's pretty simple, right? It's 1s2. So what I'm gonna do once again to remind you guys how we work on this. Uh, Here is my energy diagram. So I have 1s orbital here, another 1s orbital here, right? For each helium atom. Okay. And then now, so this is heliums here, Z equal 2. So that's one atom of helium. Remember, what I'm doing here is I'm building the molecular orbitals for a molecule of He2, which means that I'm bringing together two atoms of helium to build a molecule of helium. So since we agree that the electronic distribution is 1s2, I'm going to simply add two electrons here in the first level. Okay. So when I combine these two orbitals, as I said, if we combine two atomic orbitals, we should be getting two molecular orbitals. One of these molecular orbitals will be bonding, and the second one will be anti-bonding, which we know is hiding energy, right? Bonding is combination in phase, out of anti-bonding is out of phase, okay? So isn't it sigma bonds, 1s sigma anti-bonds? I haven't gotten there yet. So combination in phase leading to one bonding and combination out of phase leading to one anti-bonding, okay? Now we're gonna see how they look like once again. So very quickly, guys, remember this is a 1s orbital. And again, we did this in the last class. I'm repeating this because uh, I want you guys to really know this well. Combining two 1s in phase leads to an amplitude which is reinforced, right? So they are both in phase. So they are kind of like merging together to form an orbital which looks like this, okay? That's an in-phase combination, an orbital which looks like this. And we agree also that because this orbital is cylindrically symmetrical around the axis, we call this orbital a sigma bonding 1s molecular orbital. I'm gonna look at the symbol now. So that would be sigma bonding molecular orbital. Put the symbol now. Yes, okay. So that could be sigma 1s, right? So this is the bonding molecular orbital. Now the anti-bonding, remember we label as sigma star 1s, okay? And that's the combination, out of phase combination. I'm gonna add a plus symbol here so you know that we are adding them up because they are in phase. And when we have them out of phase, of course, that in that case is a subtraction. What's going to take place because precisely they are out of phase. And in that case, the out of phase combination is going to create an area in which the electron density is 0. Okay, so this would be an antibonding, sigma antibonding, two different phases. I'm showing once again the shading refers, guys, to the sign of the wave function. Okay, there is electron density in both. In case if you have electrons there will be electron density in both orbitals. It's just different shading. Okay, so guys, remember once again, out of phase combination is creating here an area with 0 electron density. We call this a nodal plane. So there is a nodal plane here. Okay, that's a plane in which there is 0 electron density, and I am going to write here the probability density. Once again, remember, is the square of the wave function. So now look at the symbol right away, so everybody can remember that later on. That's something that's important also to remember. So the square of the wave function, which is what I just showed there. Okay, so that's the electron density. Remember, that's the probability density, and here equals 0. Okay, in any nodal plane. How do you know when we have a nodal plane? Whenever there is a change in the sign of the wave function, whenever there is a change, there is an area with 0 electron density. That's a nodal plane. Okay. So my antibonding orbital, the sigma star, looks like this. And now my next question, guys, is going to be how many electrons should I place in my molecular orbital diagram for the molecule of He2? How many electrons should I fill now in my molecular orbital diagram? So the total of 4 electrons, because there are 2 electrons here in one atom, and there is another 2 electrons in the second atom. That's a total of 4. So I'm going to place 2 electrons here, and I'm going to place 2 electrons here. That's a total of 4. So the H2 electronic configuration for a molecule of H2, according to molecular orbital theory, would be sigma 1s2, meaning that there are 2 electrons in the sigma 1s2, and then sigma star 1s2. So that would be the electronic distribution for an He2 molecule according to molecular orbital theory. And then we also learned in the previous class to calculate the bond order. Remember, bond order being half of the electrons in bonding minus electrons in anti-bonding orbitals. So the bond order for the molecule of He2 would be what? How many electrons do we have here in bonding molecular orbitals? 2 electrons minus 2 electrons in anti-bonding. That is going to be the total of obviously 0. So the bond order for He2 is 0, which basically means that it's very unlikely to find a He2 molecule in nature. Okay, so the dissociation energy of an H2 molecule will be very, very, very low. So they are, let's say in different words, it's more stable for this molecule to have helium as a single atoms, that's as a molecule itself. Okay. Any questions? So are electrons in the same orbital opposites of the wave function in general? I am a bit confused. I'm not understanding the question, David. Electrons in the same orbital opposite. Oh, no, this means that they have a spin pair. Okay, so they have pair spins. Spins is it's a nuclear spin. It's a property of each electron. So I'm drawing them opposite because electrons in every orbital will have pair spin. Okay, that's what I mean by that. So in each orbital, you have two electrons, and these two electrons will have paired spin. That has nothing to do with the wave function, okay? So in this orbital over here looks like this, meaning that these two electrons there will be electron density here in this orbital, there will be electron density here, and there will be zero electron density right in the middle. That's what I mean by that. That's how this molecular orbital looks like. Whereas in the bonding, the two electrons, there will be electron density found all over this area. There is zero nodal plane here. The more nodal planes you have in an orbital, the higher the energy of it. Okay? Is that clear now? Okay, good. Okay, guys, I want to move on now and go ahead, and I want you guys to do with me the molecular orbitals diagrams for the molecule of Be2, okay, and the atomic number for beryllium is 4, okay. So let's do the molecular orbital for Be2. So you guys should start working at home. So the electronic configuration for Be2, that is correct, is 1s2, 2s2. Is that right? Yes, good. So I'm gonna say now, I'm gonna have now 1s2, 2s2, okay, first and second shell. So 1s here, and then the 2s up here. So it's 1s2, 2s2, so I'll have two electrons in each of these orbitals. So 1s2, 2s2. I'll address the question right now. Give me a second. Because that's my electronic configuration for both atoms of beryllium. Sorry, let me fix this. I'm talking about beryllium. Atomic number is 4. Yes, yes, Tammy, that's okay. Okay, guys, so this is the electronic. So I will combine both 1s and both 2s. Remember the linear combination of atomic orbitals. We combine orbitals that are similar in energy, okay? That's important to keep in mind. So that's why we combine the shell number 1 with the shell number 1 and shell number 2 with shell number 2 because they have the same energy levels. So if I linearly combine these two 1s orbitals, how many molecular orbitals should I expect out of the combination of these two? If I combine these two guys, how many should I get? If I combine these two, I should get two molecular orbitals. So one is going to be sigma bonding and one is going to be sigma anti-bonding, which we just did, okay? So I'm going to complete my diagram here. And then I'm going to say that, obviously, similarly as before, the in-phase combination leads to a sigma bonding molecular orbital, and the out-of-phase combination leads to a sigma antibonding molecular orbital. Nothing really new whatsoever. That's okay. And then I'm going to combine the 2s orbitals. So combining these two 2s orbitals, how many molecular orbitals should I expect if I combine these two 2s? So it should get two molecular orbitals, once again, one bonding and one anti-bonding. That's correct, right? So the bonding is going to be a sigma 2s. It's going to look exactly like this one. I'm going to move the shape over here for convenience. So this is going to be sigma 2s bonding. And then we have the sigma 2s antibonding up there, exactly as before. So that's the linear combination of atomic orbitals from each beryllium atom. So linearly combining a total of 4 atomic orbitals, 2 1s and 2 2s, leads to 4 molecular orbitals. 2 are bonding and 2 are antibonding. Now my question is, how many electrons are we going to place now in the molecular orbital diagram for the Be2 molecules? So that I know that is the adding up. I need to add up the electrons in each atom. So that's 4 plus 4. That's a total of 8. So that is correct. So I need to place 8 electrons in my molecular orbital diagram. So I'm going to start from bottom to top. So I should place 2 electrons here. And then I'm going to place 2 here. That's 4. I'm going to place 2 here. That's 6. And then I'll place another 2 here for a total of 8. And that's it. So my molecule of Be2 will have a electronic distribution which will be sigma 1s2, sigma star 1s2, and then we have sigma 2s2, sigma star 2s2. That would be the electronic configuration for my molecule of Be2, and then the bond order, which is half of the electrons in bonding minus electrons in anti-bonding. So how many electrons in bonding orbitals do we have here, guys? 4. So you have 2 here. This is a bonding molecular orbitals, and this is 2 more. So that's 4. And we also have 4 in anti-bonding. So 2 here and another 2 here. These are anti-bonding orbitals. So that makes for a bond order of 0. Once again, in a case like this, we are predicting based on molecular orbital theory that a molecule of Be2 is highly unlikely to exist in nature. So it would be very easy to get dissociated, okay? All right. So moving on, I'm gonna go now and focus on the next atom on the periodic table. That's gonna be Be2, boron 2, B2. The atomic number of boron is 5. Okay. So I want to build the molecular orbital diagram for boron for a B2 molecule. So let's first write the electronic configuration of B2, guys. I'm going to actually remove this and use this on the bottom. It's gonna make my life easier. Okay, so what's the electronic distribution of boron with which atomic number is 5? So that would be boron atomic number is 5. So that would be 1s2, 2s2, 2p1. So it's more or less what I have here, except for I need to add an extra electron here in the second shell, right? That's going to be the 2p orbital. So there's going to be a p orbital here. It's going to be a p orbital 2p, right? So I'm going to say 2p1 here. And there will be only one electron in there. So that's a total of 5. So 2, 4, 5. Right, that is correct. So with that in mind, I'm going to combine now. I'm going to remove this since we are doing a new problem. So I don't want anyone to be confused. So if we combine two boron atoms to form a Be2 molecule, we're talking about now combining the 1s with the 1s. So obviously combining two 1s leads to two molecular orbital, one bonding 1s, one anti-bonding 1s. Sigma star. We combine also the 2s orbitals. A combination of two s orbital leads once again to two molecular orbitals, one bonding sigma 2s looking like this, one anti-bonding sigma 2s looking like this. And then we are going to combine the two p orbitals. Remember, a p orbital looks like this, okay? And we went over this, I believe, in the last class. So combining two p orbitals in phase, meaning adding them up. The combination of in phasing leads to, obviously, same phase here, guys, same phase here. By the way, before I combine that, I want to ask, how many, if any, nodal planes do we have in a p orbital? I'm gonna type it on the chat. How many nodal planes are there in a p orbital? That is correct. There is one nodal plane, guys, right here, okay? In every p orbital, there is a nodal plane. Right here, there is a nodal plane, okay? So that's a plane with zero electron density. And the reason for that is, once again, is because there is a node here, a point with zero electron density, okay? So these two are in phase, these two are out of phase. So the resulting molecular orbital will look like this. It will have a nodal plane exactly as the one on the p orbitals, and then it will have an area of bonding uh, above that nodal plane, and there is going to be another bonding area below the nodal plane, okay? That's how this molecular orbital is going to look like. And how did we name in the previous class an orbital, a molecular orbital looking like this? What's the name of that? How did we label that molecular orbital, guys? Pi molecular orbital, that is correct. So that's a pi. I'm going to say that's a pi. So that's a pi bonding molecular orbital. I'm going to look for the symbol to show you right away. So pi px, I'm going to say, okay. Remember, we only combine orbitals that are similar in energy and they have the right symmetry, right? So I combine these two, and that leads to in-phase combination of pi bonding molecular orbital. So that's going to be an orbital with lower energy as its atomic orbitals. So that's a pi bonding molecular orbital in-phase combination once again. And that pi bonding molecular orbital is going to look like this. Okay, now combining them out of phase, that's subtraction because they have different phasing. So in that case, guys, look here, the obviously out of phase means they have opposite phasing. So they will be combining these two orbitals like this, right? So these two adding up will create another plane here because obviously there is a change in the sign of the wave function, same thing over here, and already there is another plane here. So the resulting molecular orbital, we have two nodal planes, okay? Something we did in the previous class, but I wanted to make sure that you guys would really remember this today. So practicing is the best way. So the resulting antibonding molecular orbital is going to look like this. Okay, so and that would be pi antibonding molecular orbital. So this could be an antibonding molecular orbital with higher energy. Once again, guys, the reason for the higher energy, there is only a nodal plane in the pi bonding, and there are two nodal planes in the antibonding. So clearly the antibonding is higher in energy than the bonding. Okay. So once again, combining 1s and 1s, that leads to two molecular orbital, one sigma bonding, one sigma antibonding, combining 2s and 2s, two molecular orbitals, one sigma bonding, one antibonding, and combining 2p and 2p, that leads to two molecular orbitals, one pi bonding and one pi antibonding. Okay, so how many electrons total should I accommodate now in my molecular orbital diagram? So I need to add the number of electrons from each atom. So I have 5 electrons here, another 5 here, that's a total of 10. So I'm going to start from bottom to top, filling up. Okay, so I'm going to say 2 here, another 2 here, 2 here, another 2 here. So that's 8, and 2 more here, that makes 10. Okay, so 2, 4, 6, 8, 10. So the electron distribution for B2, that would be sigma 1s 2, sigma star 1s 2. Then we have sigma 2s and sigma star 2s. And then finally we have IPX2. Okay. One second, please. I'll take a question now. So the electronic distribution for a B2 molecule, according to molecular orbital theory, could be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi px2. Okay, guys, what would be the bond order for the molecule of B2? How many electrons in bonding molecular orbitals do we have in this MO diagram? So it's a total of, correct, that's 6. You have 2 electrons here, another 2 here, that's 4, another 2 here, that's 6. And how many do we have in anti-bonding molecular orbitals? That's a total of 4. So we have 2 here and another 2 here. So the third anti-bonding is empty, right? So 4. So that makes for a bond order of 1. So means that the B2 molecule is likely to be found in nature. Okay. Somebody had a question. Ruth, did you have a question?
Can you hear me?
Yes, I can.
Okay, perfect. So just to make sure, Professor, why didn't you fill out the antibonding for the last part, the electron? Why do we
So
have 10 electrons?
there are 5 electrons here in one atom. There are another 5 here. So 5 plus 5 is 10. So the
Oh,
total number of electrons that I need to fill up here is 10. So I have 2, 4, 6, 8, and 10.
oh, okay. If I will have, let's say, in the case I have 8 electrons, then I have to fill out 8 electrons inside too.
You gotta add the total number of electrons from each atom that you're bringing together to form a molecule, right? This atom has a total of 5 electrons. This one has another 5. 5 plus 5 is 10. So I need to fill out 10 in my molecular orbital. Molecular
Yeah.
orbitals are orbitals occupying the space of the molecules, right? So how many electrons there will be in a B2 molecule? 10 electrons, because each B atom has 5. 5 plus 5 is 10, right?
Yeah, that makes sense. Thank you.
That's the total number of electrons in the new molecule. So that's what you need to think. How many electrons are there going to be in my new molecule? So does that mean the bond order can only be 1 or 0? No, it's been 1 or 0 for the examples that we have seen, but you'll see quickly that it's not. So guys, next, let's do the molecule of C2. Carbon, the atomic number is 6. Okay, so what would be the electronic configuration of carbon? Once again, so that would be 1s2, 2s2, and then what else? 2p2, correct? So meaning that there will be 2p2, so we need to make 2p orbitals here instead of 1. Remember, guys, we fill up atomic orbitals when they have the same energy, which means we call them degenerate orbitals. We fill them one at a time, right? So in this case for carbon, so 2, 4, 5, and 6. Each p orbital will have 1 electron. So we don't have 2 electrons in one p orbital, because how many p orbitals do we have, guys, in the second shell? What's the number of p orbitals in shell number 2? 3 p orbitals, right? And they are 90 degrees from one another, and they have the same energy level. So we fill electrons 1 in each at a time, right? So that is how we do it. So in this case, we have 2. So 2, 4, 5, 6, 2, 4. Ruth, I think you have your microphone on. Could you please mute it? Thank you. Uh, so that's a total of 3. Okay, so combining the 1s is going to lead to the same result, uh, right? That's not a problem. So I'm going to delete the electrons just not to make this confusing, because I want to fill it up with you guys again. So if I combine from one carbon with another carbon, 2 1s orbitals, we get 2 molecular orbitals, 1 bonding and 1 antibonding. If I combine 2s orbitals, same thing, we get a sigma bonding and a sigma antibonding. Now, I'm going to look at the 2p. I said the 2px looks like this. I'm going to now put here 2px. So I'm going to be more specific now. More specific, because I want everybody to understand what we are doing here, obviously. So I'm going to call this y, 2py. And then remember that I said we have 3p orbitals. They are 90-degree angle from one another. So the 2px is going to be oriented like this, as showing on the screen. So that's not a problem. That's exactly what we just did for B2. The 2py, on the other hand, will be 90 degrees from px, so that would be something like this, right? So that would be the orientation of the 2py, okay? So because of this, I combine orbitals with the same symmetry, right? So if I combine two p orbitals from one carbon atom and two p orbitals for the second carbon atom, how many p orbitals, how many molecular orbitals should I get at the very end if I combine two on two? So if I combine two on two, I must get four, right? The total number of atomic orbitals that I am combining is four. So if I combine four atomic orbitals, in this case, 2p from one carbon atom and another 2p for the second carbon atom, the total number of atomic orbitals is four. So I'm writing here on the chat, atomic orbitals, the total is four. Then I get molecular orbitals, four. And from these four, we know that two are going to be bonding and two are going to be anti-bonding. Clearly, guys, combining in phase, once again, two p orbitals in phase, that's going to lead to a bonding molecular orbital. And this bonding molecular orbital is going to be also a pi bonding looking exactly like this, just 90 degrees from the one that we had before. So I'm going to show now a more accurate picture of this. So this is the in-phase combination. So that would be something like this, right? To be more precise. So that could be a pi bonding molecular orbital resulting from the combination of the two px. So I'm 2py, sorry. So it's going to be pi py. And the anti-bonding would be exactly the same thing, just with two nodal plane, right? So it could be gonna do it anyways in case you guys don't know. So let me combine now out of phase of the py, so everybody knows what I'm doing. So out of phase combination, once again, they have different sign of the wave function. So I need to turn this around, obviously, right? That could be out of phase combination, and then this will lead to a pi antibonding molecular orbital, which is going to look more or less like this. Then we have a nodal plane here and another nodal plane over here, 90 degrees from each other. And then we have all the disruptive interactions reflected here. Okay, so that would be a pi star py. Okay. So combining in phase 2px leads to 2 pi px, one bonding, one anti-bonding. Combining 2py and 2py leads to two molecular orbitals, pi py, pi antibonding py. Okay, so they are gonna have the same the same energy level. So it would be something like this. Is the angle of the planes? Yes, it is. Very important. You need to see the angles, Kirby. You need to know that they are 90 degrees from one another. That's very important because that's the whole point. That's why you combine only X with X and Y with Y, because they don't have the same orientation. And that's why it's important, the angle. Okay, so in phase combination, the PYX, so the pi PX. Out of phase, an in phase combination of the PY, the pi PY, okay? So pi PX here, and then pi PY here. Both bonding molecular orbitals, which are pi. I'm gonna try to place here the draw to make it look as it should. Okay, that's how it looks like. And then we have on top another two antibonding orbitals, so the pi antibonding, which everybody should know now how they look like. Okay, so we have now, once again, I'm gonna review this quickly. We are combining 4 atomic p orbitals, okay? Because of that, we get 4 molecular orbitals, the same bonding, the same number of molecular orbitals as atomic orbitals we combine, okay? So in phase combination leads to 2 bonding molecular orbitals, px and py, and they look like this. Out of phase combination leads to 2 antibonding molecular orbitals looking like this, because we combine x with x and y with y because they have the right symmetry and orientation. So this could be the molecular orbitals, guys. Once again, we have a total in one carbon atom, we have 1, 2, 3, 4 orbitals. In the second carbon atom, we have 1, 2, 3, 4 orbitals. That's a total of 4 and 4, 8 orbitals. If I am combining 8 atomic orbitals, I must get 8 molecular orbitals. So that's 1, 2, 3, 4, 5, 6, 7, 8, right? So 7 atomic orbitals, I'm sorry, 8 atomic orbitals, 8 molecular orbitals. And now my question is, how many electrons are we going to place in this C2 molecular orbital? So I need to add, that is correct, the total number of electrons in each carbon atom, because I have 6 in each of them. The total number is 12. So I'm going to fill up my molecular orbital diagram with 12 electrons from bottom to top. So I'm going to place 2 here, 4, 6, 8, and I'm gonna do this differently. I want you guys to pay attention, because even though the end result is the same, I like to do it well. So I'm gonna 9, 10, because they have the same energy. Therefore, I must place 1 in each, and then 11 and 12. Okay. So the electronic distribution of a C2 molecule will be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Then we have pi px2, and finally we have pi py. So the pi antibonding orbitals, that is correct, are there, but they are empty, okay? So guys, what would be the bond order for the C2 molecules? How many electrons do we have in bonding molecular orbitals for the C2 molecules? Okay, so we have 8 electrons in bonding. So this is a bonding 2, another bonding 4, 6, and 8. How many in anti-bonding? We have an antibonding here 2 and another antibonding here 2. That's 4. So the bond order is 2, meaning that a C2 molecule is likely to be found. There might be double bond character in between these two carbon atoms, meaning that the bond in between both of them is strong and it will be shorter as compared to a single bond. Okay, so any questions so far? Okay, so let's move on next to the example of the molecule of nitrogen. The atomic number of nitrogen is 7. A sigma 1s. Yes. Thank you for that. So guys, there was a mistake here. So I really appreciate that, Harita, for letting me know. It is a sigma 1s. No one told me. So you guys gotta pay attention to that. Didn't copy it, so thank you for pointing that out. Okay, here we go. All right, guys. So now we're gonna move on to nitrogen. Okay, so nitrogen is in atomic number is 7. So we are kind of increasing the complexity of this problem because now we have what would be the electronic distribution for the molecule of nitrogen. Okay, so that is correct. That would be 1s2, 2s2, 2p3, right? So let's do that together once again. I'm gonna change here nitrogen is 7. So 1s2, so we have the 1s orbitals, 2s2, where we have the 2s orbitals, so nothing different really here. And then we have 2p3, so I'm gonna delete this because now the picture is different. So we'll have 2p3, so I'm gonna say 1p orbital, another p orbital, and then a third. Remember, they have the same energy level. I'm gonna level this up just in case. So we have here 3 p orbitals. We also have another 3 on this side here. So I'm gonna kind of like fix this. So now we have px, py, and pz. So we have them here. All right, so this is good. And now we just have to add one more. So we have the 2py, the 2px, and the last one here, which is also, once again, 90-degree angle from the other two, right? Remember that. Okay, so we have 3 electrons in each p orbital. I'm sorry, in the p orbital. So because they have the same energy level, they are 90-degree angle for one another. What we're going to do, obviously, is to add 1 electron in each of them. Okay, it's something we know from Gen Chem. So I have 1 electron here, 1 electron here, and 1 electron here. That's a total of 3. So now we are combining 3 p orbitals from one nitrogen atom and another 3 p orbital from the second nitrogen atom, so a total of 6. How many molecular orbitals should I expect, guys? if I combine 3p orbitals from one nitrogen and another 3p orbital from the second nitrogen atom, how many molecular orbitals should I expect? I should be expecting a total of 6 molecular orbitals. That is correct. Okay. So 3 will be bonding and 3 will be anti-bonding, right? So combination of the px is here already. Pi bonding px and pi anti-bonding px. Combination of the py is here too, in phase, pi bonding py, out of phase, pi anti-bonding py. So I only need to add now the pz, which are the last ones. Remember that p orbitals are once again 90-degree angle from one another. So the third p orbital will be in this orientation pretty much. Okay. So I'm gonna put them on the diagram so everybody understands what's going on here. The third p orbital is here. So combining these p orbitals in phase, meaning that they are facing one another with the same phasing. So that would be something like this. Okay, so combining them in phase meaning that once again the two lobes facing one another have the same phase. That will lead to a bonding molecular orbital. I don't know if I'm going to be able to draw it. I hope I will. Let me see how can I do this. It could look pretty much like this. That's a combination of two PZ. Does the order of YX, no, it doesn't matter. What I care who are the most is that you guys know the orientation, okay? So guys, this is the combination, in this case, the ones that I label as PZ. The combination of these two leads to this bonding molecular orbital. Does this look like a sigma or a pi molecular orbital? This one here. How do you think this look like? Imagine that this is just an area which is exactly, you know what, let me see. I'm gonna do a much better job with this. 1 second. So, it looks like a sigma. That is correct. Okay, so this is how it should be looking like, okay? I try to do a better job here, drawing this. That looks prettier, okay? This is exactly how I wanted it to look. So that's exactly looks like a sigma because it's cylindrically symmetrical. Now, guys, how many nodal planes do we have in this sigma molecular orbital? How many nodal planes do we have there? So remember the nodal planes is, so this is a sigma PZ, okay? How many nodal planes do we find there? Several answers. Guys, a nodal plane is an area with zero electron density, any area with a sign of the wave function change. So here is another, there is a nodal plane because it is a change of the sign of the wave function here. And obviously there is another nodal plane. Okay, so there are two nodal planes in this sigma bonding molecular orbitals. So the resulting molecular orbital here is sigma bonding, which I'm gonna sorry, I'm gonna just delete this because we're still not doing this, and my apologies. Oh. So I had already my two bonding pi. I need to place my sigma pi. For nitrogen, I'm gonna place the sigma slightly above the pi. Okay, nitrogen is atomic number 7. Okay, so that's gonna be the sigma PZ bonding molecular orbital, okay, which you guys should know like looks like this. And then I have obviously an anti-bonding, which in this case is going to be hiding energy. Okay, so sigma is just how we label the orbital, okay? And we label the orbital as they resemble in a sheet. So this looks like a sigma bond. Look at the sigma bond here. A pi bond has a nodal plane across the axis here. See? Look here. This pi bond has no nodal plane here. The nodal plane is just right here. Okay? So it's cylindrically symmetrical around the axis. So the nuclei are here and here. In between the two nuclei, there is no change in the sign of the wave function. It looks like a sigma bond. Okay? And then, guys, we have the sigma anti-bonding up here. Okay? Sigma anti-bonding up there. So that could be something we need to take care of that too. Sigma anti-bonding. Yes, they are necessary because that's how you show where these orbitals are coming from, okay? And then up here we'll have the star PZ. Okay, up here. Guys, sigma star, I'm gonna draw it here quickly so everybody knows. So this is the sigma bonding in phase addition. So when we add them out of phase, obviously the lobes facing each other will be with opposite sign of the wave function. So I'm going to turn this around. And then because of that, I'll have an area here of no electron density because these two will cancel out. So therefore, this is going to be something like this. And the opposite. I'll answer the question right now. Give me 1 second. Okay, so this is how the sigma anti-bonding is going to look like, guys, in case you had questions. It would be the sigma star. So guys, the bottom line here is a couple of things. I'm going to summarize this now. Let me answer the question first. Does sigma pz have higher energy than pi px and pi py? Yes, because that's what comes out of the calculations for atoms with atomic numbers below 7. The order here is inverted when the atomic order is from A to or larger. That's also related to the electronegativity of these atoms and how closer are these pi atomic orbitals to the nuclei. Okay. All right, guys. So once again, 3 p orbitals and 3 p orbitals, a total of 6 p orbitals. If I combine 6 p orbitals, I will get 6 molecular orbitals. Okay. Now, 3 of them will be bonding and 3 of them will be anti-bonding because 3 of them are resulting from in-phase addition and 3 from out-of-phase addition. The 3 bonding, 2 are pi and 1 is sigma because of the orientation pi bonding, sigma bonding, PZ. And from the 3 anti-bonding, 2 are pi and 1 is sigma for the same reasons, because I am combining X with X Y with Y, and X and Z with Z. And the orientation of the p orbitals, which are like this, will result in sigma bonding and sigma antibonding. So 3 bonding, 3 antibonding, 2 pi 1 sigma, 2 pi 1 sigma. Okay? Again, because nitrogen has an atomic number of 7, so it's lower than 8, we are going to place the pi here lowering energy. Okay? And now you'll see a little later why is this relevant in the first place. Now, okay, so we have built the diagram completely right now. So my next question is, how many electrons should we place in my molecular orbital diagram for the N2 molecules? How many electrons should I place in my molecular orbital diagram for N2? So that would be a total of 14 because each nitrogen has 7 electrons. So 2, 4, 7, 9, 11, 14 electrons. Okay? So if I need to place 14 electrons, I'm going to start adding from the bottom to the top, 2 at a time, until I get to 14. So 2 here, 4, 6, 8. Okay, so 8. So I'm going to start now as I should. So I'm going to say 9, 10, 11, 12, and then 13 and 14. Okay? So shouldn't sigma antibonding? No. The order in the antibonding is always going to be like this. Once again, this come out of calculations. So, guys, 2, 4, 6, 8, 10, 12, 14. Okay? So, the electronic configuration of a molecule of N2 will be, I'm going to put this slightly smaller, will be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, nothing new. Now we have pi px2, pi py2, and finally we'll have sigma pc2. So that would be the electronic configuration for the molecule of N2. All right, so what would be now, let's do the bond order according to molecular orbital theory of N2, guys. So that would be half of how many electrons in bonding molecular orbitals do we have from the nitrogen molecule? How many electrons in bonding molecular orbitals? That would be a total of 10. So we have 2 here, 4, 6, 8, and 10. How many in anti-bonding molecular orbitals? 4, so we have 1 here, 2, and another 2 here, that's 4. That's it, these anti-bonding are empty, so the bond order is 3. Okay, that means once again that the bond order for a molecule of N2 is predicting a triple bond, is predicting a very strong bond in between 2 nitrogen atoms, which is actually real. The nitrogen molecule is highly stable with a very high dissociation energy. Okay? Any questions so far, guys? Okay, no questions? Okay, so I'm gonna minimize, I'm gonna just reduce the size of this, and then what I'm gonna do is uh, I'm gonna get rid of this. Move it over here just in case you guys want to take a look at it later. And then let's do the same analysis that we just did. Uh, in this case, we were looking into the molecule of N2. Now we're going to do the same analysis by looking into the molecule of O2. Okay. So the atomic number of oxygen is 8. Okay. So the electronic configuration of oxygen would be 1s2, 2s2, 2p4. So I need to add 1 electron in the p orbitals. Okay. So right here, I'm going to add 1. Okay. Now, my molecular orbital diagram, if I combine, how many atomic orbitals do I see in this oxygen atom? How many total of atomic orbitals do I see here? Guys, how many atomic orbitals do we have in one oxygen atom? How many atomic orbitals? Total of 5 atomic orbitals, right? 1 atomic orbital, 2, 3, 4, 5. 5 in each. Total of molecular orbital must be 10, right? So 1, 2, 3, 4, 7, and 10. So 1s and 2s produces 2, 1 bonding and 1 antibonding. 2s and 2s produces 2, 1 bonding and 1 antibonding. 3p and 3p will produce 6 molecular orbitals, 3 bonding and 3 antibonding, okay? So, and the same, 1 will be pi, 2 will be sigma, so nothing really changes. The one thing that is going to change, and that's what I'm doing this, and I show you now something that is going to be hopefully interesting for you guys. The one thing that is going to change is that because oxygen has an atomic number of 8, which is larger than 7, it doesn't matter, Kobe, it doesn't matter, okay? Because we are looking at molecular orbitals here. So we are talking at orbitals in the molecule, okay? So that doesn't really matter. You can place it wherever you want, but you always put it in the first one that you write there. It's just a matter of convenience, okay? They have the same energy. So guys, here is what happens, okay? So because oxygen, once again, has a atomic number of 8, what's gonna happen here is that the sigma Pc is gonna be lower in energy than the pi, Py, and Px. That's the difference. And every atom with an atomic number larger than 8, you're going to follow the same pattern. The sigma will be lower in energy as compared to the pi. Everything else is exactly the same. We just reverse the order of these two. That's all we need to do. Okay, so we have the sigma and the pi. pi px, pi py, and sigma pz. Okay? That's the only thing that is going to change. So now, same question again. How many electrons should we place in the molecular orbital diagram of the O2 molecule? 16, 8 from each oxygen atom, right? So I'm gonna go filling up from bottom to top 16. So we have 2 here, 4, 6, 8, 10. No, no, the anti-bonding does not change. So now we add one at a time here, guys. Remember, okay? Just putting them like this to save time. So once again, we need a total of 16. So we have 2, 4, 6, 8, 10, 12, 14. So I am missing 2. And this is very interesting. So I'm going to add 1 here and another one here. I'm going to color code this so everybody can see this. Now, why I can't just... Okay, exactly. Okay, guys, so a couple of things. And this is going to be a very interesting thing for you guys to see, okay? So let's calculate the bond order. First of all, what would be the electronic configuration of the molecule of oxygen? So let's write this down. I'm going to copy and paste this below. So the molecule of O2, atomic number 8, will be sigma 1s, sigma star 1s 2, sigma 2s, 2 star 2s2. Now we have the order here change, right? So now we have sigma pz2, right? P phi y and px2. Yes, yes, Karen. Whenever we have elements with a atomic number of 8 or larger, and then we have pi antibonding PC1. Sorry, PY and PX. I apologize. Pi antibonding PX1 and pi antibonding PY1. Okay, so I want you guys to look here because this is going to be something for you guys to, I want everybody to pay attention. So let's say we draw the molecule of O2 according to valence bond theory, okay? So if we were to draw the molecule of oxygen according to valence bond theory, remember Oxygen is in the second period of the periodic table, so I'm expecting in a molecule oxygen to follow the octet rule, so we have a double bond, and then I will have two lone pairs in each oxygen atom. Okay, we practiced this a lot in class before. Everybody agrees on that. Everybody is following, guys. So we have an O2 molecule. It's a molecule in which you have an oxygen with two lone pairs, okay? And I asked so many times when we were looking at organic molecules, according to valence bond theory, in which orbitals are the lone pairs located and so forth, which was correct for organic molecules. But here is a thing. According to valence bond theory, and once again, I'm gonna color code this, oxygen is a molecule having the lone pairs of electrons paired. Okay, so two in one orbitals and two in one orbitals. So they are pair electrons. And according to the molecular orbital diagram here, what is the bond order for the molecule of oxygen? Guys, what would be the bond order? So let's see how many electrons in bonding orbitals: 2, 4, 6, 8, 10. In antibonding, we have 2, 4, 5, 6. 10 minus 6 is 4. The bond order is 2. Okay, so the bond order for O2 equals 2, predicting an oxygen molecule exists, obviously, predicting that it might be double bond. I'm gonna also follow the predictions on molecular orbital here, and you will see how interesting this is turning out. According to molecular orbitals, the last two electrons in the oxygen molecule are unpaired electrons, so meaning that each of them is in the different orbitals. Okay, unpaired electrons. Okay, so I am going, before I go ahead, I'm gonna label this orbital, something you're gonna need for next semester, particularly for organic too. So guys, the orbital here, look at the PC orbital. This orbital here, the sigma PC nitrogen, is the highest occupied molecular orbital. So that means it's the molecular orbital hiding energy with electrons on it. Okay, highest occupied molecular orbital is the sigma pz. And that's very important because remember, for reactions, the electrons that are hiding energy are the ones that can be given for reactions. For oxygen, the HOMO is here. These are the highest occupied molecular orbital, the pi antibonding. Okay. And then the antibondings that are empty, so the lowest empty orbitals, so the orbitals that are empty, which are lowering energy, those are called LUMO, lowest unoccupied molecular orbital. That means the molecular orbital that is lowering energy and is of the empty ones. Okay, so from the empty orbitals, the one lowering energy, that's called the LUMO. That's very important, guys, because once again, if a molecule is going to react given the electrons, if this molecule is going to give the electrons to another molecule, those electrons will be coming from the HOMO orbitals. If the molecule is going to accept electrons for a new bond, the orbitals used for this bonding will be now the LUMO. Okay, that's why we need to know that. So in the oxygen, the HOMO here and the LUMO is the sigma star. Okay, that's it here in the oxygen. So here is the thing. According to valence bond theory, An oxygen molecule has all of its electrons are paired electrons, 2 and 2. However, according to molecular orbital theory, the electrons in the home orbitals are unpaired electrons. So oxygen has 2 unpaired electrons. And it happens so there is, I'm gonna type this on the chat, there is a property of molecules called paramagnetism. So molecules can be classified into paramagnetic and diamagnetics. Okay, so paramagnetic molecules, they they are attracted to magnetic fields. Whereas diamagnetic molecules are not. So it's just a physical property that paramagnetic molecules are molecules that are attracted to a magnetic field and diamagnetics are not, right? And it's also known that paramagnetic molecules, they have unpaired electrons, and diamagnetic molecules, they have paired electrons. So what happened is the following, guys. According to valence bond theory, oxygen would be paramagnetic because it has 2 lone pairs, so no unpaired electrons here whatsoever. According to molecular orbital theory, there are 2 unpaired electrons here on the home orbitals, which means that according to molecular orbital theory, oxygen is paramagnetic. So when you do the experiment, and I'll show you now, you can do an experiment in which you can actually uh, flush liquid oxygen. I'll show you the slide now. So you can flush liquid oxygen through 2 dipoles of a magnet. Okay, with the liquid oxygen, when it's not in the magnetic field, the molecules of oxygen are completely disoriented. They are randomly rotating. Whereas, amazingly, when the liquid oxygen goes through the magnets of the dipoles of this magnet, the oxygen molecules are capable of orienting themselves toward the magnetic field. And actually, the liquid oxygen stays suspended in the air, which is pretty fascinating, which actually proves that oxygen in reality is a paramagnetic substance. So if you do the same experiment with nitrogen, nitrogen is diamagnetic. It doesn't stay suspended. It just flows through. With that being said, the point of this is that this is an example in which molecular orbital theory explained very well the chemical properties and the physical properties of these molecules, in this case of the molecule of oxygen, because valence bond theory fails to explain why oxygen is paramagnetic. Because according to valence bond theory, oxygen will be diamagnetic. And the fact that oxygen is paramagnetic, the fact that oxygen has unpaired electrons means a lot, because it also means that oxygen reacts in many different ways as it would if it were to be diamagnetic. Okay, so this is a one really pretty example to show you guys how relevant is molecular orbital theory to explain the electronic distribution of molecules and how we can relate that to explain how these molecules behave in nature. Okay, so we have been talking in the class about homonuclear diatomic molecules, which means that we are talking about homonuclear. We have been discussing examples of a molecule formed by two atoms, right? And that's a homo and two atoms that are the same, okay? So this is the simplest example for molecular orbital theory. This can get extremely complex if we go to molecules like, for example, nitrogen oxide or carbon monoxide or CO2, right? Because now to make the molecular orbitals of these molecules which have different electronegativities, which means that different energy orbitals will be combined, or when you have more than one atom to combine, that add up a really complex equation to linearly combine atomic orbitals. So is this property in any way related to hybridization? No, no. Hybridization is valence bond theory, nothing to do to molecular orbital theory. That property can only be explained through molecular orbital theory because according to valence bond theory, oxygen will never have unpaired electrons, okay? So the bottom line, guys, is that the same as you can see with the oxygen molecules, which I hope you can see how useful and how accurate molecular orbital could be to explain how the electrons are structured in these molecules, then you can expand that reasoning to organic molecules, which is the whole point, right? So we are going to learn in the next class how we can envision the electrons in organic molecules according to molecular orbital theory, and that would be pretty useful for you guys later on next semester and in organic 2 to understand the reactions between organic molecules. Many of them can only be explained through molecular orbital theory, not through valence bond theory. Once again, valence bond theory is pretty good. It can explain really well the structure of many molecules in the vast majority of them, but there are examples in which the electrons are delocalized, for which molecular orbital theory will do a much better job, and that's why we need to know this, okay? So with that, I'm gonna end today's class. I'm gonna stop recording